I'm Ming Lao. So welcome to our Crunch Group seminar this week. So today we have two talks. So the first one is a joint talk. Professor Sukumar and Professor Srivas are going to give us a talk on the exact imposition of boundary conditions with distance functions in physics-informed deep neural networks. So Professor Sukumar holds a PhD from Northwestern University, and he's currently a professor in civil and environmental engineering at UC Davis. And Professor Sukumar's research focuses on mesh-free methods, novel discretization, and fracture mechanics and finite elements, among many other fields. And Professor Srivastava is an associate professor in mechanical material and aerospace engineering department at Illinois Institute of Technology, IIT, not that IIT. And he holds a PhD from the University of California, San Diego. And Professor Srivastava has received the NSF Career Award and is currently an associate editor of Mechanics of Material Journal. And his research interests are in the area of wave propagation, homogenization theory, among many other fields. So please join me and welcome our speakers for the first talk.
Thanks. I just want to, sorry, Ankit, before you start, I just want to ask everyone who is not giving a talk to please mute your mic so that there's no echo. Ankit, you can start your talk, please.
Yeah, I just have a question. So Sukumar would start, but I have a question from Ming Lang. So how much time is there for this joint talk?
Oh, we're pretty flexible about time, so please don't worry about it.
But not 2 hours, but you can go over the hour.
Yeah, we'll shoot for an hour. I think so. Is the plan at least, right? Okay, so thanks for the invite to both of us, from all of you. And so I'm going to talk about how to impose boundary conditions with distance functions in physics-informed neural networks. First of all, I would like to acknowledge discussions with Anand Reddy, Eric Chen, and Kai Harman. And this talk is, and of course, Ankit's Career Award from NSF. And before sort of proceeding, this talk is entirely based on this paper which is shown here, and I'll just show you a quick. So this is the archive paper, a preprint. So entirely this talk is based on this article. So you can follow pretty much as we go along. I've sort of sketched the talk along those lines. So what is shown here on these pictures is just a preview of what is going to appear afterwards. So here is shown a distance. An approximate distance function to a polygonal mesh, which is actually the map of Bhutan. And I picked up this EPS from a free website. And this is the approximate distance function to annulus. Basically, you have concentric circles, and this is the approximate distance function. This is a neural network shown here. And this is the sort of solution we get for a Laplace problem, where we impose the displacement condition u is equal to 2 and u is equal to 1 on the inner and outer boundaries. And so you can see here that these boundary conditions are exactly imposed. So that is the main motivation. And my own viewpoint from here is to actually look at how can you impose boundary conditions exactly on complex geometries, in particular in 2D and 3D, since I'm coming from the mesh-free arena. But of course, this the notion of imposing boundary conditions also extends to higher dimensional problems. And one of the examples will be shown by Ankit later on. So let me get started with the outline. So here I'm going to give you a very broad outline so that you can it provides context to what is given in the archive paper. And also it provides context for those who are not familiar with mesh-free methods and their evolution over the past 30 years, since I've been working in this area for about 25 years or so. And tied to that is also some developments in generalized barycentric coordinates. And I'm going to use one of the constructions, in fact, to construct an approximate distance function so that it ties in with that. And within the barycentric coordinates regime, I'll also explain, at least go over one of the constructions, which is based on entropy methods, which is what I worked on myself, more from the data approximation point of view. But it has some nice connections to convex analysis, convex geometry, and also probability theory also. Because one knows about, in machine learning, one knows about the place of entropy and how to do sort of learning algorithms based on entropy models, as well as loss functions based on sort of relative entropy or sort of maximum likelihood. So there could be other connections also which can emanate, and it might resonate, I thought. So the first topic is essentially that, which is shown here. And then I go into the theory of R functions, which is the basis of most of the talk thereafter. I'll talk about that and then go into approximate distance functions. I've lost my mouse somehow, so I can't point it, so then I'll go into distance functions and first introduce you to essentially the exact distance function and tell you why we need approximate distance functions, and show through two constructions, one through what is known as R equivalence and the other is the mean value potentials, which has connections to barycentric coordinates. And the final topic is the crux of the talk in some sense. But to get there, I'd sort of give you this background on 1, 2, 3. And that is how do you construct boundary conditions for Dirichlet and mixed boundary conditions. And there are three ingredients to get there. The first is basically what are normalizing functions and a solution structure. And you combine that with transfinite interpolation over curves and surfaces to get to what we want. So that is the essence of my talk. And in the 5, 6, 7 is what Ankit is going to cover. And he'll introduce you to the JAX library, and it's used to basically implement in Google Colab. We have used the Google Colab platform to implement the method itself, the pin method as we have done in this case. And he'll showcase examples in 1D, 2D, and the last example is in 4D. And he'll close with some conclusions and outlook. Okay, so let's start with mesh-free methods and GBCs. So here's the two problems broadly that we focus on. And here I've shown you the strong form and the weak form, or the variational principle in this case, for two linear boundary value problems that he will focus on. So the first is the Poisson equation, which is given above, where you have the Dirichlet boundary conditions, and corresponding to that is the variational principle, where you seek the solution U, which is the minimizer of a potential energy function, which is shown there. And we're looking for the space of functions which are in H1, or functions in H1, and they must satisfy the exact boundary conditions for it to be kinematically admissible. So you're searching the correct space. So that's the first form. And so in collocation, one looks at the strong form directly, and you use the strong form and collocated points to solve the boundary value problem. Whereas when you use a RIDS method, which are the two approaches which are widely used in deep RIDS and deep collocation, we use the variational principle and to create an approximate solution to that. And the other problem is yes, biharmonic problem, and a prototypical example in mechanics, at least in solid mechanics, is plate bending. So here we're looking for the biharmonic operator, which is del square here, which is U is equal to F is the PDE. And here with the variational principle is given below. And again, you can identify pi as a potential energy functional. So here I'm using the clamped conditions. So both U is 0 and the normal derivative of U is 0 on the boundary. And again, for kinematic admissibility, both must be satisfied for any ansatz. So therefore, this becomes a bit more difficult, as I'll mention afterwards, with finite element. And that's one of the reasons why also mesh-free methods have come to the fore. Okay, so here's a quick overview of sort of mesh-free versus FEM. So here's a mesh shown here, or a bunch of scattered nodes. You have an underlying mesh, and I'm showing you a Delaunay FEM mesh here. So these are called what I call hat functions. And on the right, again, the same scattered nodes, but now I have a diffuse representation. So you can think of this like a Gaussian function, which has compact support. So those are typical mesh-free basis functions. So they have compact support. They don't use an underlying mesh in the construction. And associated with that is in the bottom, I show you the stiffness matrix that arises, say, if you're solving the elasticity problem, where for triangles, I goes from 1 to 3 in each data, in either 3 nodes. Whereas for mesh-free methods, there could be many more nodes which contribute at a Gauss point, for instance. So that's the basic point, that the FEM is based on a grid, and the basis functions are constructed on each element per se. Whereas here, there's no notion of mapping, and everything is constructed in the physical space itself. Okay, so let's go back to take a look at mesh-free schemes from a broader perspective, and especially in relation to collocation. One of the earlier studies was done by radial basis functions, and there's an extensive sort of study, a 2-part paper by Kanza with application to CFD primarily, and where he used collocation using global radial basis functions, right? And so that was the point, and where he used collocation in the interior and on the boundary. So one of the challenges with radial basis functions in this setting is that there's a, how do you choose the parameter, the shape parameter, what they call, which is the support of the basis functions, which they have to be different in the interior compared to the boundary, because then the condition number could become adversely affected, because you get a linear system of equations. They are linearly independent globally, but locally they could become dependent, of course, by this construction. So that was one viewpoint of just looking at direct collocation. And there have been a skew of methods more from the Galerkin point of view or the Ritz point of view. And among them, a popular sort of approximation scheme is the moving least squares approximants. This goes back to work by Nerelis and Touzeau in CompMech in '92, diffuse, and that gave rise to element-free Galerkin by Belishko, and there have been many other methods which all use moving least squares. So these do not interpolate data, and so therefore one of the issues which arises in these methods is basically imposition of boundary conditions. And my own work has been on natural neighbor and the entropy approximants. So this has a nice property that you can impose boundary conditions as you do with finite elements. And these are some of the papers which are relevant to this study. And I'll talk about the entropy method afterwards. So this is the broad sort of scope of mesh-free methods. And the next slide will tell you why they've been useful or what their promise has been, at least to start with. So they provide a flexible approximant that do not rely on a mesh. So there's no isoparametric mapping involved in the construction. So this permits directly sort of the issues of mesh entanglement sort of go away or are mitigated to a large extent. So therefore, you can do extremely large deformations for nonlinear continua overall. And the point I raised before is that with FEM, it's very difficult to construct C1 approximations on meshes. You have to go to much higher sort of basis functions and unknowns if you want to go towards the Clough-Tosher construction and others, of course. So, but if you want to solve this with mesh-free, it's much more simpler. You just use weight functions that are, CK smooth, and you'll get CK basis functions. And in terms of application, of course, they've been applied to plate bending, strain gradient theories, the Kirchhoff-Love theories, and also phase field models of fracture. So those are the pros, of course. So what are the cons? So the cons are they're non-polynomial, unlike FEM. So they're always non-polynomial in the physical space, and in the context of moving least squares, they are also non-interpolatory. So we need a mechanism to impose boundary conditions, and especially Dirichlet boundary conditions, because natural boundary conditions are taken care of by the Ritz method or the weak form if you do Galerkin approach. So that's the main argument. That's the main sort of limitation. So there's been a host of methods which have come about since the mid-90s on imposing Dirichlet boundary conditions, including Lagrange multipliers, penalty methods, or Nietzsche's formulations, and each of them have their strengths and weaknesses. But this still persists to be an issue, of course, especially with non-convex boundaries and complicated geometries. It becomes a major issue to impose them. Along with that, the other issue is that if you want to enable robustness and accuracy, since these functions are non-polynomial, the numerical integration also becomes a delicate issue. How do you maintain robustness and accuracy in the presence of constraint problems, for example? And that also is an issue. So essentially, you have the boundary conditions and basically numerical integration, besides being linearly independent and those issues which arise. Okay, so now coming to sort of pin-based sort of mesh-free methods, this is my one slide, and I just listed some of the main sort of site sort of references here, but of course there are many more which are provided in the paper. So, this goes back to the early work of Lajaris and initially, and then of course McFarlane and Mahan. So even in Lajaris' work, they try to actually impose boundary conditions sort of exactly, though of course on very simple geometries. But he recognizes that you can have two terms if you want to impose Dirichlet boundary conditions, where the first term takes care of the exact imposition of boundary conditions, and the second term takes care of which has the neural network approximation in it. And the subsequent paper, I think it was in 2000, they recognized that, okay, in general, one cannot do that. The first term, only for simple geometries you can do that. So the second paper actually talks about using two neural networks, one for imposing the boundary conditions. They use a Gaussian network, and the second one is the neural network for solving it. And in fact, afterwards, more recently, the same approach, but in the context of using distance functions, has also been used by Berg and I forget the second author's name. So I think in the paper, I think neurocomputing it was in. That paper also
I think.
Yeah, Nystrom. Yeah, now I remember. Yeah, Nystrom, Berg and Nystrom. It's a very nice paper, which I found to be interesting also. in this context. And of course, then all of you are familiar with the work of Ricey et al. and also in JCP, and also Waynon and you in Comp Math Stats. The first one talks about the collocation to various nonlinear and time-dependent problems. And of course, Waynon's work is on the deep RIDS method. And of course, since then, there have been many, many developments. But these are the sort of main references where I just quote here for reference. Okay, so going back to the pros, we all know that, of course, given the background, that if you can do mesh-free collocation, it makes it really, really interesting, because now you don't need a mesh at all in some sense. And you can also you can solve very different types of boundary value problems, essentially using a similar code in some sense. And the primary emphasis is on low dimensional problems, but of course the beauty is that you can do higher dimensional problems where mesh generation becomes impossible. And therefore you have to have some strategy to work with that. And in that case, of course, PIN is very, very powerful. So the nice thing that one accrues from this construction, or the PIN construction, is that the approximation is very flexible because it's done via composition. So you have essentially a global approximation, but it has local features which can capture H and R adaptive solutions. Since many folks have shown that you can recover essentially FEM solutions in practice. So those are the pros as I see it. Okay, so what are some of the cons and some of the potential remedies as I see it? So I view sort of PIN as in the context of what is going to follow as an embedded domain method where you want to decouple geometry and approximation. So this has come about in the past 10, 15 years on a lot of interest in methods of what are called embedded interface or embedded domain methods, or also called cut cell methods or cut FEM methods, and all these methods where they want to decouple geometry and approximation so that you can, there the emphasis was on using sort of simpler meshes, so to speak, or Cartesian meshes, and you cut that by some complicated geometry. And there the issues basically become of linear independence of basis functions and of numerical integration. But of course, the nice thing about PIN and the construction and the advances so far is that you bypass the entire numerical integration issue, which is a huge deal, of course. And so one can focus pretty much, the emphasis of this work is on the geometry part, right? And how do you impose boundary conditions? So that is the main focus here. So what we're going to use are basically R functions to start with, and that's primarily the emphasis, to impose boundary conditions exactly in deep collocation and deep RIDS. And especially in deep collocation, it becomes essential if you want to impose, and this is being a long-standing issue, though people have tackled Dirichlet boundary conditions, it's much more challenging to do Neumann boundary conditions, and of course, Robin thereafter. And the benefits are that then the loss function will only contain only the PDS loss term, and that, Ankit will go through this in more detail, of course, when he gets to the actual formulation and the terms involved. So last issue is of how do you estimate, sort of my own interest in how do you sort of, which a question might be often asked is how do you enable systematic improvability, right? With FEM methods, or if you look at plane waves, for example, where there's a single knob or two knobs, in this case, H and P adaptivity, where you can get better solutions or more accurate solutions in general. So one of course, strategy, if you have very complicated domains, geometries with internal and external boundaries, where you might have joints, you might have holes, you might have basically open spaces, or you might have even multi-interfaces or interfaces to deal with. So then you have to look at such geometries. Domain decomposition sort of is a good starting point because in a sense it becomes essential to some extent. So that is the backdrop of everything. And now let's move to barycentric coordinates and try to link it up together. So there's been a lot of work on, especially starting from computer graphics in the early 2000s and my own work in this area, on constructing shape functions, so to speak, on polygons and polyhedra. So here's just a brief shown as a polygon here. And we define this approximation of a scalar function UH through a linear combination of basis functions phi ui. So these are called convex approximations because they are non-negative, and they form a partition of unity, and they can reproduce linear functions. So together with partition of unity and linear reproducing conditions, this suffices in a Galerkin method to get optimal convergence in Sobolev norms. Okay, so what are the applications? So this going back to what the initial work of Watchpress, where he developed rational finite element basis functions directly on the mesh itself. So you give me a polygonal element, you can construct what are called rational Watchpress basis functions. The most sort of interesting sort of development in this area, which came about in computer graphics, was the mean value coordinates by Mike Floater, who used basically the mean value theorem of calculus to develop, again, coordinates. What they call coordinates are basically shape functions or basis functions in this context, right? So they have been used in various applications, and here I show you a few of them. The first on the left is transfinite interpolation, where you want to interpolate over smooth surfaces or curves. And then the next one in the middle is for color interpolation, where you're given, obviously a very non-convex polygon, both interior and outside, and then you can use a single sort of, because mean value coordinates extends to even outside the polygon smoothly, and they only see 0 at the vertices. So therefore you can do color interpolation and also mesh deformation. If you want to, you enclose your object inside a cage, which is a polyhedron, and now you just move you do isoparametric mapping essentially to move, to deform the horse. But because of the convexity property, then the horse will never go outside the cage, which is the attractive feature. So this idea of barycentric coordinates has been taken one step further in the notion of harmonic coordinates. So this was done by the folks at Pixar Studio. And what they did was to actually solve the Laplace equation with the appropriate boundary conditions on the vertices or on the faces of the boundary. And Ankit will show you an example of these harmonic coordinates, which we have sort of solved using PIN essentially. And my own work is on entropy coordinates, which I proposed in 2004. And also I'll show you subsequently its extension to mesh-free basis functions by Ortiz and Marino Arroyo. Okay, so going back to entropy, so some of you will be familiar with this. So we consider a discrete set of events, x1 to xn. We assign a possibility or probability of each event. This goes back to the work of Shannon and afterwards of James. So Shannon's work in communication theory. We associate an uncertainty of each event as minus log pi, and as of course p goes towards 1, the uncertainty decreases, and when pi is 1, of course there's no uncertainty. So the expected value is what is known as the Shannon entropy, is minus pi log pi, and that's so what are the nice properties? It's that it's an average uncertainty, it's a concave functional, so therefore there's a single or unique maxima for this function. So it's good to, when you have convex or concave functions, then it's good to apply obviously optimization because you're looking for a single solution. And what James postulated was, if you want to do inductive inference, then you basically maximize the entropy subject to your constraints. So we know if you toss a die, you have summation of pi is equal to 1, and then the expected value is something called E. Let's call it E. And now based on this information, this becomes, you can't find a solution because there are infinite solutions, because you have only 2 equations. So this gives us this maximization procedure gives you the least bias distribution. So here's an example. You have a die with sum to 1, and you're given the expected value is E. Now for different values of E, you solve the entropy problem, which is using Lagrange multipliers. So you get basically an exponential like solution, which is in the form of a partition function in statistical mechanics. And this is the solution essentially. So if the average value is 3.5, then you can see from here that all the values are 1/6. But if not, the die is loaded, then different values have to be assigned. And how do you assign it in the most least biased way? So my contribution here was to draw this connection to barycentric coordinates, to take a polygon now, which has these 5 vertices here. And then you say, okay, you maximize the entropy and think of the basis functions as a discrete probability distribution. Summation, they sum to 1, and then the reproducing conditions, which I showed you before, is given here. And that gives you these entropy basis functions on these different shapes. And you can also do non-convex polygon, which I did with Kai Harman many years ago. Okay, now the extension to mesh-free approximations is interesting. So now what happens if you have a scattered set of nodes? Because going back to my previous slide here, so here entropy gives you a global solution. It gives you all the basis functions are non-zero at a point. So if you have a bunch of scattered nodes and you apply entropy, then all the basis functions will be non-zero. There won't be any locality associated with that. So the initial connection is going back to the work of Rajan in discrete computational geometry, where he said, okay, if you actually minimize this function, which is like an internal energy, a quadratic term in terms of phi xi minus x squared, then what you obtain with the same constraints as I showed you before, phi should be positive, they sum to 1, and they reproduce x. What you find is that this solution is exactly the Delaunay basis functions. So if you solve this optimization problem, then you recover the Delaunay basis functions. So that was the sort of the rationale or the approach which was used by Arroyo and Ortiz, where they said, okay, you can think of a free energy G, which is like beta times U minus S, or U minus, if you think of Gibbs free energy, It's like U minus TS, where the temperature, the beta parameter is like 1 by temperature. So they were looking at it from that viewpoint as basically as a thermal limit of when beta essentially goes to infinity. So when beta goes to infinity, you recover the only the Delaunay interpolant, and when in the other limit, you get basically entropy. And so for finite temperature, they thought of, okay, this is like blending these two approximations. So you can see that beta is like a regularization parameter here, right? That's one viewpoint to look at it when you have these two terms. And now, of course, you have to choose beta, right? For in some sense, for whenever you want to construct the approximation. So the other viewpoint of this is what I showed in this paper which is shown in reference 17 below, is to say, okay, you can actually rewrite that expression precisely in this form, in terms of the relative entropy or the Kullback-Leibler divergence, where phi I log phi I by Wi is the expression. Now, Wi turns out to be is a Gaussian. So what you can view this as basically trying to find out a distribution phi I, which is as close to the Gaussian as possible, but which also satisfies these constraints. So now this provides you sort of more flexibility. And one of the applications we have used this for is to devise Wi's so that they basically become 0 on a polygonal mesh. And we have used R functions for that in a mesh-free method a few years ago. So this provides more flexibility in some sense on one hand. But of course, here you have to choose beta because the Gaussian, the Gaussian support size have to be fixed for every, you pick the X size, the node centers, and beta can be changed. Beta can change. It need not be a constant for every node, but you have to assign it. And of course, we don't know what is the optimal value, right? So in fact, if you think of going back to radial basis functions, which I talked to you before, where you have basically Gaussian functions like Wi, then PIN provides you a method if you use Gaussian networks to actually optimize beta for you yourself. And people have, in fact, Arroyo has done work on trying to optimize beta through variational adaptivity on MaxEnt itself. But it's much more complicated because the problem becomes non-convex and non-linear. Whereas with PIN, of course, given what are the algorithms available for automatic differentiation and backprop, then it provides at least a solution which is very good overall.
I have a question. So the setting here is Rn, right? So in other words, are we talking that omega is an infinite domain, or is it there's
no. Okay. Probably I do not,
because so I don't see my question is like if I think of SPH, for example, or whatever, I don't see a scale here. I don't see a horizon. I don't see,
Yeah. Okay. Probably I was going too fast.
Okay.
So let me just go a step back. So here capital D is the dimension, okay, on the top. So let's take 2 dimension for this, right, for argument's sake. So it's easy to explain. So D is 2, I fix it, but now I have coordinates x1 to xn. So think of a square, a square domain in 2 dimensions, and I distribute a bunch of points inside the domain, right, and on the boundary. So those are my x1 to xn. So think of small n as 1,000, just for argument's sake, right? So 1,000 nodes inside the unit square, for example. Now, if I use entropy alone, I will get 1,000 basis functions, right? But they become very, very flat, of course, right? Because they are 1,000, they all sum to 1, right? Now, what this provides is locality. It provides locality is the question you are raising, the horizon stuff, right? The horizon is through beta. Because for very large values of beta, right, you almost get Delaunay basis functions, right?
Right.
That's the point. So let me go back here, right?
So 1 over square root of beta is the size, is the compact.
Yes, exactly, right. So because you can see from here, when you take beta as, beta is 1 by beta times S, right? So when beta goes to infinity, entropy drops off and you get only basically the internal energy, only the Delaunay appears, right? And in the other limit, when beta goes to 0, then of course the internal energy drops and you get only entropy. So there's basically a blending, right, by this term. By beta is you're blending basically on one extreme you have Delaunay and the other extreme you have entropy, right? And so and you get natural blending based on this construction. So you don't have to do any physical blending in terms of the approximations, right? And you can also tune beta, right? Where you want regions where you want, where you want you want more resolution, you can make beta sort of more sharp or localized, or it could be flatter elsewhere and so on and so forth, right? So those are things, but you have to pick it, of course, right? But PIN provides you a way to actually solve those, get those from the solution, right? That's the point I was going to raise before, that it provides you as part of the solution procedure, it tells you what the approximating functions are. Whereas in traditional mesh-free methods, you have to pick the approximation functions a priori because you want linearly independent functions and so on and so forth, right? So I don't know if that was clear enough or not.
Yeah, clear. Thank you. I was missing the length scale. Thanks.
Yeah. Beta gives you the length scale. So e raised to minus beta. Basically, it's a Gaussian, right? So that's it. So what are the benefits of this? Is that because it's in some sense this is like a generalization of B-splines on structured meshes to unstructured meshes, right? But only for the linear part, for linear reproducing. So it has these nice facet reducing properties, which I'll mention next in the next slide. It has the convex hull property. You can represent nicely without sort of the Gibbs phenomena or the Runge phenomena, even sharply discontinuous functions. And if you do like dynamic problems, you can get a positive definite mass matrix because the phi's are strictly non-negative. So therefore, the mass matrix entries will also be positive. So that's basically outlined here. Okay, so the point I was mentioning before is that if you look at MLS basis functions, they are non-interpolatory, but more importantly, they're not convex. So what happens is that, as shown on the left figure, they become non-zero on the boundary. So therefore, these methods based on Lagrange multipliers or coupling with FEM and all that have come about in the context of this method, right? And whereas with Maxent, you can directly impose it because it has the interior basis functions vanish on the boundary. So even though the functions are not polynomial, nor they are interpolatory actually, but they can reproduce X and 1 on the boundary. So you can impose it as if you're doing FEM on the boundary, essentially. So that's.
Sorry, I have another question. So I think Nat Trask, who has done the generalized moving least square. He did that while he was part of the crunch group at Brown.
Oh, okay, yeah, I met him. Yeah.
So in his case, he will have the same problem as MLS, right? So he will still have to.
Yes.
Boundary conditions, yeah.
Yeah, I think this is common to all mesh-free methods, right? I mean, literally. I mean, barring the ones which are convex, right? Of course, because with convexity, you get this automatically. It's proven in this paper by Arroyo and Ortiz that for convex basis functions, that you get the boundary condition imposition can be done as an FEM, as long as they can reproduce linear functions or affine functions. So that is what has been shown before, right?
Yeah.
So but of course, in the context of Galerkin or Ritz in the mesh-free context, their concern was mostly only Dirichlet boundary conditions because they were not doing collocation, of course, right? Because with collocation, there are other issues, of course, which arise, right? You have to be careful about. But in RIDS itself, there are so many issues on just imposing boundary conditions on complicated geometries, right? So that's the point. Okay, so that took a long time actually to explain. So okay, let's get to some of the topics which are relevant to here. So I'll try to go a bit faster. Okay, so this goes back to work of what are called R functions. This goes to the work of Reveshev, which was mostly in the Russian literature, and only in the 90s or so on, it came about in the English literature, and largely, I just mentioned here just a couple of references, but there are many more given in the archive preprint. And the first one which appeared is the work of Reveshev and Shaiko, but there have been other papers by him, and there are also review articles by Vadim Shapiro from Madison in Acta Numerica, as well as many of his groups, of folks from his group have solved actually boundary value problems using this. So this is more in the sort of spirit of what I call embedded methods, where they use an underlying sort of B-spline or a radial basis function as basis functions, and then you hit it with some boundary, and then they use R functions to impose the boundary conditions. So what does this do? This provides a sort of the representation of geometry using implicit functions. So sort of in the spirit of level set methods, one can think of course, but more towards sign distance functions. So what is the R functions? It's a real valued function f, whose sign only depends on its arguments, known as R function. So anything that depends only on its sign is known as an R function. So here I just consider things which live in R2. At least the points are living in R2. So what makes it powerful is that if you can think of them as sort of regular sort of Boolean operations, become as you think of them as binary, sort of binary on the real plane or the three-dimensional or n-dimensional plane. So taking on 0 and 1 values by assigning different regions to 0 and 1, then you can represent basically solids, which are solid modeling in semi-analytic geometry. So you can represent as a composition of union, intersection, and negation, essentially, any solid. So that was the point, and some examples. So if you take a function x, y, then if I know the sign of x and y, so x and y are just two arbitrary variables, then you know that f1 must be, the sign of f1 essentially. And likewise, if you know x squared plus y squared, then doesn't matter what x and y are, we know always f2 is always going to be positive or non-negative. But if you take f3 in the entire, for any value of x and y, then of course I cannot say the same thing. And of course, you take any sine or cosine and all that, and it will again be not an R function, but if you take an exponential, it will be an R function. So that's just a quick overview of this. Now, what are the Boolean set operations and the connections to sort of set theory? So first is what is called known as R disjunction, which is the union operation. We sort of symbolically represent by the V term, and then the conjunction operation, which is the intersection, and which is by the wedge operator. And then you have negation or the complement, right? So these are the three fundamental building blocks in set theory, which you can use to represent any basically operations from this, right? Can be derived from this. And one of the things we're going to use is R equivalence. And so if you take an example of a unit disk in R2, I can define an R function, which is just omega, where I define the function omega as 1 minus x squared minus y squared. So it is positive in the interior of the disk, 0 on this boundary, and negative outside. So I can think of this Boolean 0 and 1. So I can assign 1 to be the interior and the boundary, and 0 to be the exterior and the boundary also. So that is my Boolean operation on this. So there are basically generalizations of this R function. The simplest is the min function, which is the R conjunction, and the max function, which is the R disjunction. But there are generalizations which are shown here, which can be seen as sort of a triangle inequality, right? You think of WA and omega A and omega B as lengths of the edges of a triangle, right? Then this basically is a generalization of that it basically gives you the triangle inequality in this form. And if you choose alpha is equal to 1, you get the min function or the max function, which is the simplest R disjunction and R conjunction functions that are possible. So that's one route to it. And here I show a Venn diagram to give you a sort of a clear illustration of union and sort of disjunction, the connection. So if you take two sets A and B, then the union is basically given by this sort of region, which is the V operator or the disjunction, and the intersection is given by the max function, right, of the two, and that is given by this operator, this picture here, and the negation is the complement of A. So I'm assuming that the entire space is R2, so that's the complement. Whatever remains outside is the complement. And now you can construct an equivalence operation, which is the intersection of A and B, and with its union, which is of its complements. So that is the equivalence which I'll use afterwards. Okay, so that is just the background on sort of R functions itself. Now, what do we do with it is a question. So that leads us to what are called distance functions and their properties. So we define, if you take S as a solid or an object with boundary del S, then you define N as the outward unit, N as the outward unit normal, and I define nu as the inward unit normal to del S. So the exact distance we know gives the shortest distance from X to the boundary with, of course, we know that D must be identically equal to 0 on the boundary itself. So it has many applications in solid modeling, real-time rendering, computer vision and computer graphics, and level set methods. And in fact, iconal equation is one of the applications. And also, Ankit will show you an example on that. And there's been a lot of interest in computer vision, especially recently, on deep neural networks for distance functions, construction of that itself also. Okay, so what are the exact distance has this property that it has derivative discontinuities on the medial axis. So therefore, because they're equidistant from the more than one point on the boundary, and therefore it's only C0 at that interior to the domain, and therefore you cannot use it for deep collocation with pin, for example, in this context, right? If the point where there's a derivative discontinuity is part of the boundary. So therefore, it's our desire to construct approximate distance function with suitable differential properties in S, such as it must be smooth inside so that you can apply it to higher order derivatives. It must be positive, and that's another important point, that it must be strictly positive in the interior, because we are going to impose, if you take a Dirichlet problem, for example, right? So just to illustrate, it'll come up afterwards. So for a Dirichlet problem, I can say, like a homogeneous Dirichlet problem, I can say, okay, my approximation is phi times the neural network, where phi is 0 by construction on the boundary, right? But now, of course, I don't want phi to be, it has to be positive inside the domain. Otherwise, essentially, you'll get u is equal to 0. The approximation will be identically 0 at those points. So therefore, it's very important that they be positive, right? And in terms of properties, it's also interesting to have, or at least desirable to have unimodality. So there's only a single maximum. So that are basically sort of, you can say, you can draw contours of it, which are basically extend to the boundary. So its behavior is nice when you take its derivatives also. There are less undulations on it, and it'll help to train the network in a better fashion, is my sort of interpretation of this. Okay, so what do we do next is look at approximate distance functions. Again, goes back to the work of Reveshev. So it's composed of, so if you want to compose approximate distance functions to the boundary del S. So we define phi I as the ADF to each curve or line segment to begin with, right? That's the initial construction, right? So what are the things we would like to preserve, right? Of course, we would like phi to be 0 on the boundary because it has to satisfy the exact distance relationship. And in addition, since we are going to impose sort of boundary conditions, and especially Neumann and Robin boundary conditions, it must preserve the normality condition. That is, normal derivative of the exact distance is going to be 1. So therefore, in this context, del phi by del nu, which is grad phi dotted with the inward normal vector nu, should be equal to 1. And if possible, especially if you're doing higher order problems, then it's desirable that all higher order normal derivatives vanish. And this was known as what is called normalization to the mth order. And what it says is that del phi by del v nu is equal to 1, and all higher derivatives up to, say, k is equal to 2, 3, up to m are also 0, because these are properties which are satisfied by the exact distance, but it's still an approximate distance because the exact distance will have m going to infinity, of course, right? Whereas we truncated at some point. Okay, so the consequence is that for finite m, the ADF will only match the exact distance very close to the boundary very well. But as you go further and further away, it will deviate from it, of course. But it will retain at least the desirable properties, which is what we want in the context of PIN, right? So how do you construct this? So what we do is first you construct to take a line segment, you construct a sign distance just by using the equation of the line. It's simple enough here, shown here as f. Then you construct a trimming function on top of that to truncate it, to chop it off, because it has finite length and not the whole real line. So there is a trimming function, is basically the equation of a circle where xc is the middle point. And then you can construct, this was done by Reveshev, an approximate distance function to a line segment via this formula here. And this preserves actually C2. There are other forms which are only C0, but this provides C2 away from the line segment. So these are the three ingredients which are required essentially to construct an approximate distance function to a line segment. So f, t, and phi. And using the JAX, I think when Ankit gets to it, he'll show you a JAX implementation of precisely these three formulas in code, actually. So you'll see exactly the same formulas appearing on his slide afterwards. Okay, so what does this bring to you? These are the three functions shown to you. That's the first one, the sign distance to a line. This is the trimming function, which are basically circles. And this is the approximate distance function to a line segment. So it has this property as it's 0 on the line segment, which is the white bar here. And its normal derivative is precisely 1, except at the vertices, of course, right? Because there's not well defined, the normal, right? Okay, now you do the same thing for a circular arc shown here. And again, there's a circular arc with the trimming here. And then this is what you get for, so you can see the iso contours here, which are well separated, right? So you can see that that's what you desire in a nice distance, approximate distance function. Okay, so that's the first part. So how do you construct a distance function to, say, a curve or a line segment? But of course, the ingredient is we need to combine many of these together, right? And that gets us to what is called R equivalence. So this was, again, this was proposed earlier also, but
I have a question. So the curve has to be C1, or I can have C0 curves?
Come again?
Okay, so you took can I have a line next to a semicircle that you showed? So it could be a C0 continuity.
Yes, you can join them. In fact, in the paper, I think I show you a curved triangle, for example. Okay. Is that what you mean?
Well, yeah, the continuity of the curve that we're trying to.
Yeah. The curve, it can be C0, like, because for a polygon, it's C0 only, right? The curve is C0 if you take a polygonal domain.
That's what I'm.
Yes. But of course, the curve has to be, at least C0. Yeah, okay. So then coming to the R equivalence. So how do you join basically different ADFs, what I call ADFs, which are approximate distance functions? So that is given through this formula of phi, which is phi1, phi2 divided by to the power of m and then you take the mth square root. So this is normalized up to order m. And this also has, if you look at this formula, this has this sort of inverse distance sort of appearance, the sort of LM norm of an inverse distance, because this theme will recur again afterwards when we go. What is nice about this is that this is just for two ADFs, which I've shown you. So think of a polygon, think of two lines which are joined together, right? Which is phi1 and phi2, right? But now what happens if you have a polygon, right? You have, say, 50 piecewise linear segments which are joined together, then you need to something more elegant. And in fact, this turns out to be elegant because by composition, this formula basically can be written like this, which is shown below, right? Basically the same formula essentially, right? And the proof is in one of our earlier papers of this, but it also appears probably in other Reveshev papers, in earlier Russian papers. It probably is given there also. So what is nice about that, this is an associative relationship, which I emphasize here. So it doesn't matter the order of how you take some of the other formulas which are presented in the R function literature are not associative. So then it would depend on which order you take, how you compose the different segments. Here, it doesn't matter which order you take. You can just take, as long as you have 10 segments which form the polygon, there are 10 segments, you'll get the same formula based on this expression emboxed here, right? So here are some pictures here. So I show you a triangle, I show you a square, I show you an L-shaped domain. And also then you take this, so I got this polygonal map in EPS and I converted that into a polygon inside MATLAB from this website. So you can extract the boundary edges and then you construct this sort of, based on the expression I showed you before, essentially, right? So this has 291 vertices, right? So therefore there are so many edges, and therefore you have to combine all these edges to construct one function, right, from this. And you can see that it looks pretty nice overall. So that's the first construction, right? The second idea is to also leverage things that have been done in generalized barycentric coordinates. So I mentioned to you mean value coordinates of floater. So this is shown on the left. So the nice thing about mean value coordinates is that you have vertices 1 to n on the boundary. It could be non-convex, and x is a point in the interior. And so the formula which shown here below, that is, the var phi is a weight function wi divided by a normalizing weight. So they sum to 1 basically. So w is equal to the sum of wj, where the wi's take on this form. It has this inverse of the distance from the vertex, right? Appearance, 1 by rho type of term, right? That is what appears. So what is revealing in this sort of paper and also work of Floater and Harman in 2006 afterwards is that they found out that actually w, the denominator here, w is strictly positive in the interior of any polygon, right? It is strictly positive in the interior of any polygon, and it's inverse basically. So if you take 1 by w, it is like an approximate distance function with normal derivative of half on the boundary in 2 dimensions. And this has been generalized to d dimensions by Floater afterwards. And that's, I think I mentioned that in the paper also. So what this buys you is that from this construction, you can actually get an automatic ADF without any trouble, right? Because based on this formulation here itself. And that was shown in a different way through the work of Belyaev, who connected with what are called LP distance fields, right? So I'll just show you this version here. The next slide talks about the integral formulation, right? So what is mentioned here is that you can think of this 2 by w as a distance function, right? And it has the correct normal derivative of 1 on the boundary, which is distance. So normalized to order 1, essentially, what it does, right? And this is a compact representation of wi, which is used in the code actually to construct phi. So you take w and then you just divide 2 by w and you get what you want. Okay, the other approach is to looking at these ideas for curved boundaries through what are called generalized mean value potentials, the work of what I mentioned to you, Belyev's work. So you can think of this as a sort of a generalization of the transfinite mean value interpolant of Daikin and Floater, where here you think of this as basically an integral formulation where k is a kernel function, which is 1 by distance, the integral of 1 by distance. And what Belyaev noticed is that this is a generalized sort of double layer potential, and where a specific form of a specific choice gives you the mean value coordinates. But he provided a more generalization and said, okay, if you take p is equal to 1, you get essentially this formula. And then if you project it onto the boundary, there are more steps involved in the derivation, but essentially you can write down this as a integral over the entire boundary to construct W of P, of course, in this. And then from W of P, you can construct phi. And as P gets larger and larger, you get better and better approximations, but they are all smooth to the exact distance. So, and this has been done by us in a previous paper last year on actually applying it for some interpolation problem, right? To show that you're getting better distance approximations as P gets larger and larger. Okay, so some pictures here using this MVP construction. So here's again the L-shaped domain. And again, now I construct the Bhutan map, the polygonal map using this distance function. So notice that here, if I use the polygonal formula, there's no joining and all that required. It's automatic here, right? So it gives you the entire polygon in one shot. So I don't need to go through the R function construction overall. So it's much faster, of course. But of course, in the case of an ellipse or a more propeller-like shape, which is sort of given a parametric form on the boundary, then of course you have to actually solve this problem for every point in the interior to solve the integral problem, right? Compute it numerically. Okay, so now let's get to the last part, which is the BCs and pin. I've already gone too long actually, but there are only five slides left. So, so this is a network just to lay down the notation we're going to use. So the parameters are theta, denoted by the vector theta. So I'll use, as in sort of the classical collocation, u tilde nn as the trial function in standard pin. And just to distinguish it, in our approach, we'll use with a superscript r as the nn approximation. And we'll use NNBC to be the trial function in our approach. So UNNR will feature in the construction of UNNBC, right? And for a second order problem, you can think of it like this, where it is G plus phi times U tilde R NN is the trial function, where G is a function that is composed of Dirichlet boundary conditions, assuming that we are just using Dirichlet boundary conditions, and phi is the ADF to the function. So now because on the boundary or on different pieces of the boundary phi is identically 0, then you recover G, of course, right? Wherever you prescribe G. Okay, so let's go to the ingredients, the three ingredients that I mentioned to you right in the beginning of the talk. So let's omega be an open bounded domain, and so consider a smooth function, which is an approximate distance function, and we'll call it normalized. As I mentioned to you before, it's normalized to the mth order. So what Revesher first defined were what are called normalizers to U of the mth order, why the transformation U star x is equal to U of x minus phi grad phi. So what this does essentially in words is to knock off the higher derivatives. Higher normal derivatives are basically vanish along that direction. So what it does is that on the boundary, U star is exactly U, but all the normal derivatives become 0 up to the mth order, depending on what is, depending on the value of m. And the proof for this is shown in the preprint for m is equal to 1. So what this buys you is to define what is called a solution structure. So let's assume that you're prescribed with the normal derivatives along nu to be given by these functions, u naught x, and then u1x, u2x, and so on, right? So here I'll consider only u0 and u1, of course, in the problems thereafter. So what Revesher did was to write down a generalized Taylor series expansion in the vicinity of the boundary in the normal direction. So it's like univariate sort of Taylor series, but in the direction n, or in the direction nu in this context, right? So u of x is now given as an expansion of u naught star of x, right? Plus where u naught of x is the value prescribed, then the first star is the derivative, normal derivative prescribed, and so on, right? And the last is what is called the remainder term, which is the unknown, sort of an unknown function, right? So this is a general representation of any function in the vicinity of the boundary. So this is referred to as a solution structure, which we'll use to construct the pin approximation. So let's now start off with Dirichlet. So let U is equal to G be prescribed. So now you set basically U naught star to be G, because I'm given G essentially here, and use M is equal to 0, the generalized Taylor series. So this is the first term, and the remainder term is phi times some unknown function psi 1 of x. So now you expand G, so you get this first term here, minus phi del G by del nu on the boundary, plus the remainder term, only up to the first order, I'm linearizing it. And then, of course, del G by del nu is del G by del n, because nu is equal to minus n on the boundary. So that gives you this form, which I showed you before, G plus phi times psi, where psi is the basically the approximation which we want to construct. So in our case, we are going to use, so if I write that as u tilde, then u tilde becomes my network approximation, right? And G is going to be the function that I prescribe on the boundary. So now do the same for Neumann boundary conditions. We'll sort of first start off with this sort of identity here, or this relation rather. So when you say, okay, let's assume that U star is some of normalized function, which is U of x minus phi grad phi. Now you expand this out again to the first order. You'll get one term which is shown in red here, which is equivalent to the previous term in red, and the remainder term is phi square. So therefore, so the idea here is that U star does not carry any gradient information. All the normal derivatives of U star are 0 essentially by this construction, right? And I've used, of course, here that nu is equal to minus n is grad phi to get to the relationship. And the important thing here is that I've defined this operator d1 phi, right? So d1 phi basically is the operator which acts on the boundary, and it basically is the normal derivative in the outward normal direction. So I've switched it from the inward to the outward because that's what we use typically for imposing boundary conditions for PDEs. Okay, so now if you prescribe del u by del n is equal to h, then we can again use the solution structure to write this first equation, and then use essentially what I did from the above equation to replace it by this first term right out here, because I know that 1 plus phi d1 phi of u naught does not carry any gradient. Its gradients are basically 0, or its normal derivatives are 0. So you get this expression here, and notice now essentially u1 is equal to minus h, because now I define the normal derivative as del u by del n is minus del u by del nu, which is equal to h. So therefore, you get a minus phi h here. And if you take the normal derivative of del u here, right? So if you take a normal derivative of del u, you'll precisely get it to be equal to h. Right? So that's what is the solution structure for imposing a non-zero Neumann boundary condition. And of course, if h is 0, then you recover the 0 Neumann condition, right? And we'll use in the context of DNN, we'll use u1 tilde is equal to u2 tilde is equal to this value, this expression for the. Okay, so the last ingredient is the Robin boundary condition, which is shown here. So
I have a question. I have a quick question here. So here, because you truncated Taylor, right?
Yes.
So you have is it an h square? H, I shouldn't use h, but no. Basically the spacing from the let's say delta n square, the error.
Yeah, like no, the error is because now it's like it goes as phi square, right? Basically, you can think of
phi square. Yes.
Yeah, phi square is like h kind of, right?
Right.
Direction, right? Basically, yeah. But the point is that phi square is like h, but then psi is entirely free, right? So in some sense, they have shown, at least the papers, they have shown that you can get convergent Sobolev norms by there is a function psi which will give you the right convergence rates, right? So basically, you lose convergence, right? By choosing, but how to choose psi is the question, of course, right? And the point is that here I'm going to replace psi by the neural network, and the neural network has the universal approximation theorem. So in principle, it should be able to approximate anything, right? So that was the rationale.
I was thinking more like the phi square, because if you look from above, is this an exact the? I thought you did a Taylor expansion somewhere.
Yes. So this is like the phi square times psi is like a remainder term. You can think of it like that.
Or is the whole the remainder? It's like mean value theorem.
Yeah.
I see. Yeah,
it's like a remainder term which I just go up to m is equal to, in some sense I go on to m equal to 1, right? So the m equal to 2 is the remainder, right? And I say, okay, it's something times the derivative, like we do in Taylor series expansion, right? It's something times the unknown function there, right? Which is there.
Okay. Yeah.
Hi, this is Mauro. I have a question. Is this so you can do this also with finite elements, right? Say you have a level set and the boundary doesn't align with the mesh.
Come again?
So like so if you discretize something with finite elements, but your mesh is not like the edges of the mesh are not aligned with the boundary, like the boundary is computed by a level set method, for example.
Right.
Can you use something like that?
Yeah, but I think the challenges which I've been doing for many years now with cut cell methods and other things, right? So if you look at traditional, sort of compactly supported functions, right? Like, which form a basis, right? Like, FEM or B-splines or whatever, right? So then when you have these cut cells, right, you also get linear dependency issues, right? Depending on how the cut is done. Because, the support size can become vanishingly small So when you end up with the linear system of equations, they could be very, very badly ill-conditioned, right? So that is another thing. So you need to stabilize that.
Right.
Also, so therefore, there are other issues which arise when you do these cut cell methods with FEM or other methods, right? Essentially, or B-splines or other things.
Yeah, yeah, no. What I'm asking if you can, instead of using cut cell, you can use a method like the one you're presenting.
Oh yeah, you can. But I mean, the point is that that's what has been done by the R function group, right? I mean, the people who use R functions, right? They essentially use like a structured mesh, you know. So think of a mesh which is regular with B-splines or with FEM, you can think of, and you hit it with some boundary which is circular or polygonal or whatever, right? And then you basically represent the boundary conditions through this approach.
I see.
Right, but then the next issue is, you know, you do integration on these arbitrary shapes, right?
I see.
Yeah, so there are other issues which arise, which, you know, people are working on it, including myself, on curved geometries and cubature and all those things, right? But my interest was that, okay, you know, a lot of those things are sort of circumvents all those issues, right?
Yeah.
But except the boundary condition issue. But then this could be one way of tackling the boundary condition is the sort of viewpoint, I would say, right?
Mm-hmm.
So I don't know, should I proceed or?
Yeah, and that and so is this sort of a linearization somewhat related with what's done in the shifted boundary method? Are you familiar with that?
Oh, you mean Scovasi? No.
Yeah.
But there, I think, as I recall, there they move the boundaries so that it conforms to the boundary. It conforms, right? I mean, so it's like they're modifying the problem a little bit, right? In some sense, right? So here I want to maintain exactness of whatever geometry you're giving me, right? So
I think they do a kind of extrapolation of the basis function so that you can.
Yes.
Yeah.
They do an extrapolation of the basis functions, and so they modify, you know, the sort of variational sort of setting, I would say, right?
Mm-hmm. Yeah,
right, exactly. Right.
Thanks.
Yeah. So okay, so the last ingredient which is remaining is the Robin boundary condition, and that's fairly simple to see. So for the pure Neumann problem, we had this solution structure from before, and what you'll notice now is that suppose I take the function phi c u1 tilde. So it turns out to be it's precisely minus c u1 tilde. Its normal derivative is precisely this function, right? So then you add up the two and you recover, basically you get this solution structure, which is u is equal to 1 plus phi c plus the operator d1 phi acting on u1 tilde minus phi h plus phi square u2 tilde. And now you can set both of them to be equal to the DNN approximation. And this will satisfy Robin boundary conditions. Exactly. And then I think probably Ankit might show an example also on this afterwards. Okay, so now I have provided you these solution structures, right? But now you might ask, okay, now if I have a polygonal like the Bhutan map I showed you before, and I have different boundary conditions on different edges, how do I handle that? Of course, right? That's the key ingredient, right? Which this provides. So how do you glue basically solution structures together to provide an ansatz? And that is through the notion of a transfinite interpolation, which is also inverse distance sort of interpolation you can think of. So now we have basically the boundary is composed of different subsets gamma I. The solution structure for each is denoted by ui. I'll call it I equal to 1 to n. And phi I is the ADF to gamma I, and phi is the ADF to gamma. So what is the key ingredient is using transfinite interpolation based on singular, what I call inverse distance or Shepard functions. So this has been widely used in, going back to the 90s for mesh-free methods. When you want to do interpolation through singular functions, one way is to do basically data interpolation by Shepard functions, which are singular at the point, right? And therefore they'll interpolate at the nodes itself. So this is just a generalization of that to curves and surfaces through this. So the Wi here is shown here is a function of only x, but ui's, as I showed you in the previous slide, they can be functions of x and the parameters theta. So wi's, where phi i's are the distance, approximate distance function to the power of minus mu I. And here, so they form a partition of unity. And the mu i's are 1 if you want to interpolate over the gamma I, whereas you would choose 2 if you want to interpolate over normal derivatives, for example, which is what we also do in this work. So that's the essential formula. So you can think of the general solution structure, trial function is of the form u bar, which is to impose whatever boundary conditions you have, plus the remainder term, which is shown earlier in the slides, like for example, phi square or phi1, phi2 or whatever, that term, which is going to identically satisfy basically the homogeneous form of the boundary conditions in some sense, right? So that is what is the basic solution structure. And I mentioned here the remainder term is the function of phi I, phi, and u tilde r specifically. But the for specific examples, Ankit will go over choices of UN and BC specific choices that he's made. Okay, let me stop here. I've just gone for 1 hour plus. Gosh, it's a long time. I'm sorry. So let me stop share. Okay, Ankit, you can take.
Okay, can you see my screen here?
Yes, we can see.
Okay. So I don't have much time, so I'll go quickly here. So I just want to show you a few applications, few examples for what Sukumar has discussed earlier. So let's consider this PDE problem. The first one is the PDE itself, and the other two lines show you boundary conditions. So what we are going to do is we seek the solution UX. What we're going to do is we are going to represent the solution UX in terms of another function, which is sort of, this function is a function of two other functions. So one of them is the distance function to the boundary. The boundary is basically gamma u plus gamma n, and then a neural network. Okay. And these functions will be combined in a complicated fashion depending upon the solution structure. Okay, Px is the distance function to the boundary of the domain. It could be an exact distance function or an approximate distance function. And most often we use an approximate distance function because of the fact that phi x itself may be, or the Laplacian of the phi x may be similar at various points. Okay, and then this term, which is simply a neural network here, U R N N. Okay, by construction, this term would satisfy the neural net. This approximation would automatically satisfy all the boundary conditions by design. And this includes directly boundary conditions, Neumann boundary conditions, drop-in boundary conditions, or a combination of all of them. And so we determine the NN parameters by minimizing a single loss function on the PDE. Okay, and we aim to show that minimizing a single loss function has strong benefits in the training of the neural network. Right. So we are going to use two different kinds of distance functions, as Sukumar mentioned. One comes from the R function theory, and here Sukumar also had these plots, but we are simply going to use. This is one example of creating R functions. So basically, phi1, phi2, phi3, and so on and so forth are distance functions to various parts of the boundary. So phi1 could be the distance function to this vertical line, phi2 could be the distance function to this line, and phi3 could be the distance function to this curve, and we can combine all of it to create an approximate distance function to the entire geometry. So there are these three examples here, and the other distance function, approximate distance function that we used was the mean value potential, and some examples for that as well, and some equations are given here as well, right? So basically, these two recipes would give us phi essentially. Right? The notation is this: that whenever we use u, n, and bc, we are talking about a trial function where all the boundary conditions have been satisfied. And the loss function for u, n, and bc is L, n, and bc. On the other hand, when we just use u, n, n, it basically represents a standard pin where the boundary conditions have not been a priori satisfied. And the loss function for this is simply L, n, n. I just want to show you what these look like. So for example, if you have a Dirichlet boundary condition on the boundary of the domain, then L, n, and bc would simply be a loss on the PDE in the interior of the domain. Whereas the LNN, which is the standard pin, would include a loss term for the interior of the domain and a loss term on the boundary of the domain. Okay, and we can play with the weighting of these two terms. In this paper, we don't do it except for one or two examples, because we just wanted to keep it as simple as that. We just wanted to focus on this here, LN and BC. All right, and then an approximate is fairly, I'm not going to go into any detail of it. We have shown various different architectures. For the purpose of our study, we basically use ReLU cube in the interior of the room, in the hidden nodes, and a linear activation is output there. We just use Adam algorithm, 2 to 4 hidden layers, depending upon the problem. In general, the effort here is not to find the optimal set of hyperparameters, but just showing the power of this. Then you automatically or a priori satisfy the Borel conditions. Okay. We use JAX, which is maybe some of you might be familiar with it, but it is sort of a new library where you can write functions which are very NumPy and Python based in terms of their formats. But here, a function which calculates the distance function to a straight to a line segment here, and you see the distance function here. And then these are basically distance functions to complicated geometries, which are created by joining distance functions to line segments through the equivalence operation, let's say, which has already been talked about, right? So triangle, square, hexagon, and L-shaped domain. And these are all calculated by joining distance functions, approximate distance functions using the R equivalence operation. And then we have the implementation, but everybody here would be familiar with how the neural network implementation would work. Okay, so let's talk about a few examples. So the first example I want to talk about is the deformation of a homogeneous elastic rod. So the PDE is just a one-dimensional PDE. It's defined over a domain. X1 is equal to 0 for this particular problem, and X2 is equal to 1 for this particular problem. And they've assumed some body force on this PDE. And to begin with, let's consider directly boundary conditions on the left and right hand side. So at 0, it's half, and 1, it's minus half. So how do we go about solving this problem? We create a distance function to the left boundary, and that distance function is simply x. That is an exact distance function to the left boundary, right? We don't need an approximate distance function in this case. So this is the exact distance function to the left boundary, which is x equals 0. This is an exact distance function to the right boundary, which is x equals to 1. Okay, and then we can create a composite distance function by doing various operations on phi1 and phi2. So this operation that you see in the center is a conjunction, R conjunction operation that Sukumara talked about earlier. But this operation here on the left and on the right, they are examples of R equivalence operations. So these are combining two different phis, phi1 and phi2, to create one giant phi. Okay, so that creates a distance function to the entire boundary of the domain. Now we have boundary data. On the left-hand side, the directly boundary condition is half. On the right-hand side, minus half. We need to combine it into one function as well. And that could be done through transfinite interpolation. And we get one function here, gx. Okay. Now, once we have gx and phi x, either phi a or phi b or phi c, doesn't matter. Once we have gx and phi x, we can create a solution structure here, which would satisfy automatically both of the boundary conditions at the same time. So you can see, right, at x equals to 0 or 1, this term goes away because this is 0, px is 0 on the left and the right hand, and all that remains is gx. And gx basically interpolates the boundary condition on the left and the right hand. So it satisfies exactly the boundary condition, the directly boundary condition on both sides. And we can now use a loss function, the ln and bc, to train the network, and this is what we get. These are just some various different cases. So this is the black line that you see is the exact solution, and the blue dots that you see are the UN and BC solution, the solution that we created. And you can see that it exactly satisfies the boundary condition on the left and the right hand side. The green curve that you see here is, sorry, the red curve that you see here, the red curve in both of these cases is the standard plane approximation. And everything else are our approximations where the boundary conditions have automatically been satisfied. And you can see that, I mean, we didn't do any optimization here in terms of the parameters, but you can see that the cases where the boundary conditions have been satisfied, this is the error. They lead to roughly an order of magnitude lower error compared to the standard plane approximation. Okay.
Excuse me. Yeah, this is Lulu. So what's the error here? L2 relative error, or what's the error here?
Yeah, it's a relative error. Yeah.
Actually, because for this problem, I think for standard pin, we can also achieve 10 to the -3.
Yeah, I'm sure you can. So what you would do then? Let me see if I have a slide.
10 to the -5. Let me correct Lulu. 10 to the -5.
Oh, yeah.
Yeah. So I'm sure that is possible with working with various parameters, right? So here the idea is just to compare with the same network what we can get, and with exactly the same kinds of parameters, essentially. So all the same training parameters and all the same network parameters. I'm sure that you can get lower errors by, especially by people who have more experience in training these networks. But these comparisons are fair in the sense that everything is the same in all of these networks. The number of layers is the same. The number of the step size is the same. All sorts of things. The training.
Can I ask a quick question? This is Yeonjong from Brown.
Yeah.
In your previous slide, actually, the choice of phi, because there are infinitely many choice of phi 1 and phi 2. For example, you can raise any power of phi 1 and phi 2, and actually automatically satisfy the boundary condition. So I'm wondering, have you tried the effect of those parameters? Because I feel like those are somehow leveraging how fast your solution will satisfy your boundary approaching to the true solution, so that if you somehow happen to choose the right parameter, somehow that decay level is somehow roughly at the same level of the how quickly or fast the solution approaches to your boundary. I feel like you might get a better conversions.
Oh yeah, so, I'm sure. So we haven't tried the entire gamut of possibilities. There is many things that you can do even in this phi by deriving these phis. Even the R equivalence formula, there is an M term there which creates different approximate distance functions. So we haven't looked at what is the effect on training of various different kinds of approximate distance functions. So I think that's some work for the future.
I see. Then have you observed any adversarial effect of introducing those like hard constraint on the boundary when you train neural network in this type of the form? Like the higher the M, so theoretically we will satisfy all the conditions, but when you take a derivative, then some of the field related, the gradient part might be reflected to cause some vanishing or exploding gradient.
Yeah, we have seen this. So if you have a distance function which approaches the exact distance function, an approximate distance function which is close to the exact distance function, that would have a tough time training because its derivative and its Laplacian have singularities inside of the domain, and that would have a different implement. So it's almost better to have an approximate distance function and not get close to the exact distance function.
And Kit, can you go to the next slide, please? Your first slide. You can see the red curve. Yang, you can see the red curve. You go to the training on the training. So you can see the training right away. You get there. I'm a little confused with the error because that error doesn't of course the testing error. I know that, but that doesn't necessarily correspond to this training loss. So I'm a little confused about the curve on that.
Actually, we have been also thinking about it, and we haven't gotten a great answer for that. We have seen this over and over again. So one thing is that the functions, the approximating functions, are quite different in all of these different cases, right? Like the UNN is very different from A, B, and C. So there's derivatives of the distance function in the loss itself, for example. So they are quite different from each other. But yeah, we have seen this over and over again that while the training loss, it gets to low values in UNN, the errors are higher.
I don't think the error in the I don't think the error, the red curve in the error is correct. I cannot speak about the other curves, but the red curve, I don't believe it's correct.
I can check again, but I think I have checked. It's all calculated from the same code. So, I mean, I can check again, but I'm fairly sure that it is correct. But I can get back to you and make sure that it is correct.
Ankit, quickly, you're using weights of half and half, right?
We are using the weights of half and half, on the boundary and the interior of the domain.
Yeah, so that could be, different weights could give you much better results, right?
Yeah. So I'm definitely, I'm not saying that you cannot get better results with UNN. I think it boils down to how you weight the loss term in the boundary and in the interior with UNN. And right now it's just all equally weighted. I think I'm really, so let me just show you a two-dimensional result, because that might be interesting, and I can send this presentation as well. But I wanted to show you a two-dimensional result to show you that this thing works for 2D as well. So this is an example of a steady state heat conduction. The forcing function is sine k pi x and sine k pi y. It's the two-dimensional result is a bi-unit square here. And then there's a Dirichlet boundary condition of 0 applied on the entire domain here. Okay. We create these distance functions, phi r, phi m, and phi r is created from R function theory, and phi m is created by mean value coordinates. And you can see that both are convex inside of the domain and 0 on the boundary. The one issue with these functions is that the Laplacian, for example, blows up at the vertices. So if you're doing collocation, you have to be inside a little bit inside of the domain itself. Some results here. It's again this R equivalence, MVT, and UNN. Again, I'm not saying that the UNN cannot be improved. We're just taking the same weights for the interior and the boundary of the domain. This is in fact an example of what can be done with UNN, where we have taken PDE losses. We have weighted the PDE loss and the boundary loss with different values of W. So W is a number between 0 and 1, and essentially it weights the PDE loss differently. By tuning W, you can tune the weight of these different losses. And here I show that even with UNN, as I'm sure would come as no surprise to people here, you can get to pretty low losses here. And this curve keeps going down. I'm sure that you can get to even lower losses. So the point that I'm trying to make is that it comes with the standard plane. It seems that one of the important factors is how you weight these two losses, the PD loss versus the boundary loss. And with the appropriate weight, you can get very low errors, I'm sure. So I was told that 120 is when I should strive to end. So I'm already 5 minutes ahead. So let me just show you one more thing, which is, all these results are in the paper. So please feel free to read the paper. But I want to show you one thing here, which is an example of in 4 dimension. And in 4 dimension, we consider a Poisson problem in 4 dimension. So it's basically on a bi-unit hypercube in 4 dimensions. So Poisson problem is here, and we assume that there's a forcing function on the Poisson problem, and then we assume that there is a Dirichlet boundary condition on the boundary of the domain. And this basically the interesting thing here is that we want to create an ansatz which automatically satisfies the boundary conditions on the boundary of this 4-dimensional hypercube, right? One solution for that is you take the neural network and you multiply it with a function like this, which is basically 1 minus x1 squared multiplied by 1 minus x2 squared, so on and so forth, right? And this function is 0 on the boundary of the hypercube, which means that this satisfies the Dirichlet boundary, the homogeneous Dirichlet boundary condition in this problem automatically, right? We call this the product function. But the problem here is that this has terms like x raised to the power 8 inside of the domain, so which is highly nonlinear. This term is highly nonlinear, right? What we can do is we can create an approximate distance function which isn't that highly nonlinear by using the R equivalence. So now we use the R equivalence function in 4 dimensions. Okay, and we can be sure that this approximate distance function is indeed 0 on the boundary of the domain, and this is what we get. And in this fashion, the highest power of x is x squared essentially. And we see that there is no UNN result here. There's just the 2 results: this R equivalence result and the product result. And we see that we can easily get to 10 raised to -2. This is all again. It's not absolute error, this is relative error. And the product result does not perform very well because we think that it has to do with the high nonlinearity, which is inherent in these x raised to power 8 terms essentially. Anyway, so I just wanted to show you that this is possible in higher dimensions as well. So just wanted to conclude that it's possible with these R functions and R equivalents and mean value coordinates to create distance functions for arbitrary geometries and arbitrary domains, and then use those phi values to a priori satisfy directly boundary conditions, Neumann boundary conditions, Sovereign boundary conditions, and a combination of those things, right? So that's what we're showing here in this conclusion. Some of the next problems that we are interested in are exploring scattering problems in the interior and exterior of a domain. Specifically, as I'm sure some of you are aware of, that in scattering problems like acoustic wave scattering, electromagnetic wave scattering, there is a need to impose artificial boundaries so that there are no spurious reflections inside of the domain. And generally, those are done by this process called the Dirichlet-Neumann map. And we wanted to exactly impose these boundary conditions as well for the scattering problems. And then would be interesting to look at higher dimension problems as well, 3D problems and higher dimension problems in polytopes, and as well as domain decomposition. And the suggestion that was mentioned earlier, which is to see how the distance function itself affects the training, is also interesting. So I just want to thank again Professor Panidakis for inviting both of us, and I will remember to make sure that the calculations that I did show are correct, and I'll get back to you on that.
Can I ask a question? This is Hao Sun, the next speaker. Two brief questions. The first one is, since you already have the hard enforcement of the boundary conditions, why do you still, have the loss function, the boundary condition loss in the total loss function?
So we don't have the boundary condition loss when we automatically satisfy the boundary condition. We only have boundary condition. Yeah, we don't have.
Now the second question is, I wonder whether this framework can be extended to, to take into account the special temporal problems. Let's say you have some initial condition, right? Whether you can extend this framework to account for the hard enforcement of initial conditions.
Yeah, I think so. You just create a distance function in time, and that distance function to time t equals 0, and then you can impose that initial condition, most likely. Yeah.
Okay, thank you.
Yeah.
Is there any other questions?
Yeah, I have one question. So have you tried the Burgers equation, for example, with some solutions with the sharp solution?
Yeah. Yeah, unfortunately, we haven't tried the right, Sukumar. We haven't tried.
No, we have not. We have not tried.
Yeah.
There are many things to try, of course.
Yeah, because I have actually tried this before, using basically the phi is x times 1 minus x, which is phi a in your case. Initially, I found that the performance by enforcing the exact manipulation actually the result is worse than the standard P. But finally, I do some lots of tuning, it can achieve similar results, but it's not as simply as what I expected, or not as better as I expected.
I think as someone else mentioned also, right? I mean, one has to also look into how the training affects the choice of the trial function and R functions, right? I mean, everything is training is like a black box, right? In some sense, right? So, there could be different choices and different, you don't know what's going on inside the training, right? Which is delivering it. But the general notion is that, the simpler the function is, less variations in derivatives, for example, less undulations, then the easier it is for the training to capture the solution, right? That's the, if you want to provide the network less work to do is the sort of philosophy.
Yeah.
Okay, thank you.
Any other questions?
How expensive is to compute the in 3D the distance function?
I think for convex shapes, it is not that hard. Even in higher dimensions, it's not complicated for convex shapes. I think when it's non-convex, then it becomes more complicated.
Because You can actually have, in one of the papers that I think they presented recently, one of my, from Paris Perdicaris, who was one of my students, his student showed that they can use DeepONet to learn to compute the distant function. So that takes 0 time, basically. DeepONet regress the operator. So you may want to think about actually incorporating that, because if you have an evolving geometry, that will be tricky, right? So you want to obviously have this prefabricated, pre-computed, but DeepONet could be a good combination with what you're doing.
Oh, sure. I think so.
Yeah, sure.
I think there are many avenues to explore what might be the best strategy to use, approximate distance functions, right? Because ultimately we want something fast, even in this notion, right? The notion of our functions to use was to get an analytical expression, right? And not to have an entire network do it, right? That was the speed, right? Was the main issue. And also since, it's been used in solid geometry or solid modeling, that you can compose different objects, but how do you construct different ADFs for different objects could be a topic by itself. And then that could be merged with PIN, of course, right? Like what you were suggesting, right?
Yeah. Well, one thing is that the distance function, it's good if it is convex and if it doesn't have zeros, for example, in the inside of the domain. So if it's like a strategy which gives a well-behaved distance function, approximate distance function should be fine.
Right. Yeah, that's very careful. That's therefore you cannot use any function. It has to be fairly reasonably close to the iconal solution, actually, right? So in some sense, right? Otherwise, it'll have local minima inside, and then that'll mess up everything.
Guys, thank you very much for taking the time. Sukumar, I wrote a proposal with Vadim Shapiro about the R functions about 20 years ago.
Oh my God.
But I didn't follow up. I was very intrigued, actually, because, at the time.
It's funny how things, it's how funny things come back, right? And so
yeah. Yeah. It's good stuff. Good stuff. Thank you very much.
Thanks a lot. Sorry for going over time. My mistake. And I left very little time for Ankit, unfortunately.
We will invite him back. We'll invite him back after he corrects his mistakes.
I hope he has no mistakes.
Yeah, I hope so too. Yeah.
Thanks a lot.
Yeah, thanks.
Thank you. Let's thank our speaker once again. So our next speaker is Professor Sun. So Professor Sun joined the Department of Civil and Environmental Engineering at Northeastern University as assistant professor in July 2018. He obtained his PhD from Columbia, specific interests including physics-informed AI for engineering applications, smart resilient infrastructure, advanced sensing, big data analysis, machine learning, and UQ, among many other fields. So his work has been widely reported in various media over 40 times, including MIT News, Fox News, and Science Daily. So he's also the recipient of many awards, including Forbes 30 Under 30, Top 10 Outstanding Chinese American Youth. So, so today he's going to give us a talk with title Physics-Informed Learning for Data-Driven Discovery of Governing Laws. So please join me in welcoming Professor Sun.
Thank you, Milan, for your kind introduction. Thank you, George, for your kind invitation. It's really my great honor and great privilege to have this opportunity to discuss some recent work in my group, in particular on physics-informed machine learning for data-driven discovery of unknown governing laws for dynamical systems. So my name is Hao Sun. I'm assistant professor in civil and environmental engineering and also affiliated faculty member in the Institute for Experiential AI at Northeastern University. So before I start the technical talk, the technical part of my talk, I would like to give you a very brief overview of some ongoing research in my group. So my overall goal is to leverage the power of data, machine learning, and physics principles to better understand the physical system itself. And there are two ongoing research directions in my group. The first one is physics for AI. So we actually try to leverage some known physical laws or principles together with the data to develop physics-informed machine learning models for inference prediction of the system response. So that's the first direction. The second direction is AI for physics. So in this direction, we assume we only have the data, but we have no idea about the physical law or the closed form or explicit form of the physical law or governing equation. So we try to leverage the data, to develop sort of machine learning models to discover the unknown in physics. So in this presentation, I basically focus on the second direction. So let me give you another brief overview on the ongoing sub-research topics in my group here. So the first one is on physics-informed deep learning for equation discovery. So we know that in nature we have the discrete dynamic systems or continuous dynamic systems, chaotic or nonlinear systems. So all of these systems can be described by a set of equations, and these equations are typically parsimonious. So our objective here is that suppose we don't know these closed form of equations and we try to leverage the data to discover the closed form or explicit formulation of these governing equations, giving very sparse and noisy data. So that's the first subtopic. The second is what we call it symbolic reinforcement learning and reasoning methodologies for symbolic regression and also for symbolic discovery of the governing equations, as I mentioned previously. So the concept here is to leverage the power of reinforcement learning combined with the expression tree formulation to discover the symbolic formula that can be used to describe the measurement data. So this is the second subtopic, but given the time limitation, I will basically focus on the first part, in this talk. So this is the outline of my presentation. Firstly, I will give you a brief introduction to the problem we are trying to solve, and later on followed by the physics-informed learning machines for data-driven discovery of dynamical systems. So in particular, I will talk about several different methods. The first one is PIN with sparse regression. The second is physics-informed spline learning with sparse regression. And the last one is physics-informed symbolic reasoning. And afterwards, I will talk about some discrete and continuous dynamic systems, followed by the final concluding remarks. So I'll briefly say a few words about the deep learning AI thing. I believe the entire group is already very familiar with this topic. So we see deep learning pretty much in every corner in the industry and academia nowadays. For instance, the applications include autonomous driving, speech recognition, face recognition, AlphaGo, etc. So we all know that the conventional deep learning models typically require big data to train reliable and robust predictive models, right? But when we try to apply this kind of method to address scientific problems, there are some key issues I believe the audience here is already familiar with. For instance, if we have very sparse data or noisy data, typically it's less likely to train a robust or reliable learning model. Second is on the interpretability of the model. So these models are typically black box, right, without any physical meaning. So that's the second challenge. The third one is about extrapolation or generalization issues. So given such a small amount of data, so if we train the deep learning model, so the model cannot generalize to other conditions unseen in the training data. So here comes the breakthrough PINN method, which bridges the gap between small data and some physics knowledge. So we try to leverage the power of PIN to discover the unknown physical law, and let's see how this could work. Before I start the technical introduction to the approach, so let me say a few words about the dynamical systems. So dynamical systems are seen everywhere in the world, right? Including the discrete dynamics, for instance, the double pendulum, the Lorentz attractor, and also some continuous systems such as the fluid flows or reaction diffusion systems. So all of these systems can be either described by the nonlinear ordinary differential equations or the partial differential equations in these general forms. And these systems responses might be very nonlinear, periodic, chaotic, and so forth and so on. So the conventional approach to derive the closed form of these equations are based on the first principles or some phenomenological relationship. But when we apply these first principles of phenomenological derivation to some very underexplored or less well-known systems, we are faced with many challenges and issues. So the data-driven discovery offers a new perspective to tackle this challenge. So here I have to mention several important works in the past decade. So the first paper has been published in Science, distilling freeform natural laws from experimental data. So in this paper, they used some symbolic regression method based on genetic programming to distill the natural law, for instance, the conservation law or Lagrangian formulation for some dynamical systems. However, there are some issues. For instance, such a method is typically, it has the pool scalability when the system dimension increases, and it is inapplicable to continuous systems whose governing equations are PDEs. And it is also sensitive to the measurement noise. Suppose if we have very noisy data, this method basically produces some false positive in the discovery. There are some outstanding overfitting issues. So in order to resolve some of these issues, Brunton and Ku's group from University of Washington proposed this method, SINDI, sparse identification of nonlinear dynamics. So the key concept in this method is to leverage a large space predefined candidate functions that might appear in the governing equations, then turn this overall problem into a sparse regression problem. And later on, by dealing with the sparse coefficients, they can find the parsimonious form for the governing equation. Such a method, leverages numerical differentiation, especially for the partial differential equations. There are some partial derivative terms that might, appear in the governing equation. They have to calculate the corresponding partial derivative terms based on numerical differentiation. And imagine that if we have very noisy data and we have very small amount of data sparsely sampled in the space, such numerical differentiation will induce a lot of errors in the discovery. So eventually such approach cannot deal with small data with large noise. So we are trying to address such a key challenge by developing some new methodologies. The first one I want to introduce is the PIN approach with sparse regression, and let's see how it works. The basic concept is very straightforward. So here we use a deep neural network to represent the solution of the dynamical system, let's say UVW, okay? Then followed by this automatic differentiation to build the library of predefined terms that could appear in the PDE formulation. Then we formulate the PDE in a residual form. And in this residual form, this psi is the basis function or candidate function, candidate library, and this corresponding coefficient lambda should be sparse. Then afterwards, we will turn this to a mixed variable optimization problem I will discuss later on. So here, this network is particularly designed to account for the single initial or boundary condition data. let's say we only have a single data set coming from a single initial or boundary condition, we can use this network to discover the equations or to find this lambda. And the second scenario we consider is the multi-initial or boundary condition scenario. So in this case, we might have data coming from different initial conditions or different boundary conditions. So here we propose a root branch network, root branch network to account for different initial and boundary conditions. In particular, the output of the neural network includes the response, the solution U corresponding to the certain initial or boundary conditions. Then we input all of these U solutions into the graph-based automatic differentiation to build the library. And later on, we augment all of these library functions together to build the PDE residue. Okay, so all of these collocation points in this scenario will be stacked together to produce a unified governing equation, which is actually U dot equal to psi times this sparse coefficient lambda. And afterwards, we build the total loss function, which actually includes the data loss, the physics loss. The physics loss is basically the residue from the PDE, and also the L0 regularizer. Okay, we have 3 parts. So we know that directly optimizing these parameters, theta and lambda, theta here is a trainable variable of the neural network, and lambda is a sparse PDE coefficient. So directly optimizing this objective function is not easy because this L0 norm poses some NP-hard challenge. Okay, so there might be 2 approaches to resolve this issue. The first one is to replace this L0 norm regularizer by L1 norm. So essentially, we do a relaxation of this L0 norm. We tried this approach and we found that such approach cannot guarantee the sparsity. Okay, so if we look at the solution of the discovered PDE, there are many false positives. So in order to resolve this issue, we developed this alternating direction optimization approach. So the basic concept is to decouple the optimization of these 2 variables, lambda and theta. So theta can be trained by the standard neural network training approach, ADAM or BFGS or the combined. So lambda here is solved by a sequential threshold ridge regression. So there are some rigorous procedure to find this sparse lambda that enforces the sparsity. So by doing the alternating direction optimization between these 2 variables, we can reach a high quality solution. So here I will show you some examples. And this work is actually can be found from this archive preprint. This is also a paper under review in Nature Computational Science. Let me show you some examples. The first example is the KS equation, the famous KS equation. In this equation, we have the 4th order derivative term here, U4x here. Okay, so imagine that if we use a Cindy approach to discover such an equation, then we have to use numerical differentiation, right? By doing the numerical differentiation 4 times to produce the 4th order derivative, the error will be super large. Right? So let's see how this pin with sparse regression method works. So for this approach, we designed 36 candidate functions, which consists of different combination of polynomial terms between the original solution and the derivatives. And we generate the solution using finite difference method and subsample the measurement and put different levels of noise into it, all the way up to 10%. And here I show the ground truth of the equation here and the discovered equation showing here, given 10% of noise in the measurement data. And we also compare this approach with the Cindy approach. We see for the Cindy approach, if the data is sufficient, is big, with zero noise, the SIMD approach can produce a very good discovery result. However, if the noise level increases, let's say even to 1%, and the SIMD approach basically fails, but our approach is still very robust. Even for 10% of noise, the identification of the coefficients is also very accurate with less than 1% of error. And we use much less data, about 10% data used compared to the SIMD approach. So let's take a look at the evolution of these coefficients. So I forgot to mention that we train the entire network using 3 stages. The first stage is to do a pre-training without imposing any sparsity on the lambda. Second is to apply the alternating direction optimization approach to find the sparse lambda. And later on, after the PDE structure is identified, we also do a post training, which basically identifies the coefficient for the remaining terms. So this is the evolution. We see that initially the coefficients are here and there, non-zeros, and after the ADO, and we can find the correct terms here. And the prediction of the full field response also matches the exact solution very well. And the second example is the lambda omega reaction diffusion equations, which are widely used to model the chemical biological systems. And the governing equations consist of 2 nonlinear PDEs as shown here. Here we have the G omega term. These are nonlinear terms. And for this particular examples, we design 110 candidate functions, which is also the polynomial combination of the solution and the derivatives, all the way up to the order of, I think, the 4th order. And we put 10% of noise in the data as well, and we do the discovery. Here I show the result, discovery error of the coefficient with respect to different noise levels. We can see that our approach can still work for 10% of noise case. And the measurement data here only consists of 21 low resolution snapshots, which are subsampled from the ground truth solution. And let's take a quick look at the evolution of all of these coefficients. And initially, we initialize the lambda as zeros. So you see, these are just the zeros. And as the optimization goes, we have different non-zero values here and there for UV terms. And after the alternating direction optimization, we can retain all of these terms, the correct terms, okay? And the discovered PDEs for these U and V variables under the 10% of noise are shown here. This is the ground truth, and this is the discovered equation. And the PDE structure is found correctly. And the coefficients are also very close to the ground truth. Even with 21 low resolution snapshots, we can predict the full field response very accurately. So we see here, these are the exact solutions for U and V. Here are the predictions. They match pretty well. And the next example is a fluid flow example, the vortex shading problem. The random number here we used is 100. So we place, I believe, if I remember correctly, for this case, we place 500 sensors randomly in the space to record the fluid velocity and also the viscosity values. And we try to discover the closed form for the Navier-Stokes equation in the viscosity form. And here, the ground truth solution is shown here. This is the ground truth solution for the NS equation, and this is the discovered. We see that the discovered equation matches very well with the ground truth. And our prediction of the full field response also matches the ground truth response well. And the last example here I would like to show is the Berger's equation with a shock behavior because of this small coefficient in front of this second derivative term. And in this example, I show three different initial conditions when we generate the data. And these are the three initial conditions, the sign and the Gaussian distribution, and also the cubic function as the initial conditions. And after we obtain the ground truth of the solutions, we place 26 sensors fixed at some fixed locations to obtain the measurement. Afterwards, we put 10% of noise in the measurement data. So these dots are basically the measurement data at the different sensor locations.
Hi, may I ask you a question?
Sure, yeah.
Can you actually go to the previous slide?
Yeah, just this one.
Yes, exactly. Where you're showing the governing equation for the Navier-Stokes.
Yeah.
I think there is a pressure term missing over there. I cannot see the whole. I cannot see your whole slide, but
this is a yeah. Good question. Yeah, good question. This is actually the Votowski form rather than the standard NS equation form.
Oh.
Yeah.
Oh, okay.
You see here we have a W or omega term here.
Okay. Okay.
Yeah. Yeah.
Okay. So have you actually? I would also would be happy to see if instead of this mean fields, if you actually have stochastic fields. So so if you can learn the governing equation with high fidelity simulation. So the field is actually very stochastic. So you don't really need to add noise in it. But from that stochastic fields, if you can actually find the governing equation for the mean equation would be the Ran's temporal average Ran's equation. So that would be. Do you have any thoughts, or have you done something?
Firstly, that's a very good point. We haven't yet done that, but I believe if we have the data set, let's say, that comes from the random field, and such approach can produce a equation to describe the data. Definitely, we will be happy to give it a try. That's very interesting comment. Yeah.
There are some databases available on the public. Just look at John Hopkins turbulence database.
Yes.
You will find high fidelity simulations, but not for vortex shedding. But there are other good problems as well. And there is Adagard. Also, you will find some databases for high fidelity simulation. These are stochastic fields, so that would be really interesting, I guess.
Yeah, that's a very good suggestion. Thank you, and definitely we will be happy to give it a try. Thank you.
Sure.
Yeah. Sure.
Thank you.
Sure. And let me continue with this example. These are the noisy measurement at the different sensor locations. And here, let me show you the coefficient evolution for the PDE, the potential underlying PDE. So initially, we see the non-zero coefficients here and there. So after we reaches the alternating direction optimization stage, we can actually threshold and prune the redundant terms and only keep the remaining two terms, which are actually the ground truths. And the final discovered equation is shown here. So we found that for this particular example, if we only have one single data set, let's say, without considering multiple initial and boundary conditions, if we only consider one initial and boundary condition data set, and the discovered equation, especially for the coefficients, are much worse. But we can still find the correct PDE structure, but the coefficients have much larger errors. By including different data sets coming from different initial and boundary conditions, such a problem can be alleviated. So that's our finding here. And we also predict the full field response by using the root branch network. And we found that for different initial and boundary conditions, even with very sparse data sets, we can extrapolate to the entire field with a high accuracy. The full field response error is about 3%. And we found the errors are actually present in the regions where the sharp gradient occurs. Oh, there's another example, which is actually an experimental example. So here we try to discover the equation to describe the cell dynamics. And we get the data sets from this paper. These people have done a series of experiments in the lab, considering different number of cells in a test well, and they observe the dynamics of the cells over time through imaging. And we extract the cell distribution along just 1D direction. And we try to describe the corresponding governing equation that can be describe the cell dynamics. So in particular here, we consider 4 different scenarios, 14,000 cells to 20,000 cells. So these dots are basically the testing data in the lab. And after applying our approach, we can discover the equations for different number of cells. For instance, from 14K cells to 20K cells, the corresponding partial differential equation actually follow this kind of form. And these equations, even with different coefficients, follow or match the exact form of the famous Fisher model. There's a Fisher model in the literature that has been used to describe the cell dynamics for many years. And the discovered equation exactly match the famous Fisher equation. And here I show the evolution of all of these coefficients from the pre-training to alternating direction optimization. And afterwards, we see that only 3 terms are remained. And later on, we do the post-training and consider the discovered PDE structure as known. And finally, we can get all of these coefficients. So this is the experimental example. So, and we try to validate our approach of the discovered equations. So we run the simulation. We simulate the distribution of the cells over time by using the discovered partial differential equations. And afterwards, we compare these responses with the observation data. We find that they match in general well. And we can see that the data here is pretty sparse, right? And also very noisy, right? And we only have 5 snapshots. You see that 1, 2, 3, 4 snapshots, sorry, just 4 snapshots at 4 different times. So the data, given the sparsity of the data, I think the discovery is already very good. And we try to apply such approach to discover the chaotic dynamical systems, the discrete chaotic dynamical systems as well. However, we found some issues of the pin approach. It is unable to accurately model chaotic dynamics, especially for a very long-term evolution, okay? So the reason behind it is that the approximation of the solution by the pin approach is through the global basis, okay? And there are some challenges associated with the optimization, especially we try to apply this approach to model the very chaotic response of the system along a long-term horizon. So there will be tremendous local minima when we do the optimization. And especially the large training effort is another issue. And how to tackle this challenge, we actually propose a new approach called physics-informed spline learning with sparse regression. So the basic concept behind it is very similar to PIN. So instead of using the deep neural network, we actually use the cubic splines to interpolate the solution. And the rest is almost the same, since here we use a cubic B-spline, we can also do the automatic differentiation, okay? Then to calculate the derivatives and further to reconstruct the potential physical law here, governing equation here. And we also have the data loss. So the total loss function will be the data loss plus the physics loss. And the physics loss is in a sparse regression formulation as well. There are some benefits of using the splines here, especially for discrete dynamical systems. So firstly, the approximation of the solution is done through the local basis. So we have the local basis functions, okay, along the time direction. And the second benefit is the faster convergence. We compared this approach with the pin-based approach, and we found that the convergence is much faster. And this approach has much less training effort. So we also programmed the entire approach on the GPU setting, and we compared the same, for the same problem to reach the same accuracy. This approach only needs about 1% of training time, 1 to 2% of training time, given the faster convergence. And the rest is, to solve for the spline the control point and also the sparse coefficient for the equation actually follows the same approach I introduced, which is based on the alternating direction optimization. So let me show you 2 examples. The first one is the chaotic system Lorentz attractor. We know this is a famous system widely used in many systems like the climate dynamics, chemical, biological reaction, etc. So we try to generate some noisy data to discover the closed form for the governing equation of this system. So in particular, we generate 4 different data sets corresponding to 4 different initial conditions. And the sampling rate is only 20 Hertz. That means, the data is very sparse. And we also put 10% of noise in the data set. And here are the discovered equations. We see that the equation structure as well as the corresponding coefficients match very well with the ground truth. We also use the discovered equations to simulate the response given different initial conditions. We see that they agree very well with the ground truth. So that's the first example, the Lorentz attractor. Second example is another chaotic system, the double pendulum. We know the double pendulum, the behavior of the double pendulum is very chaotic, as can be seen from this video. If you look at the trajectory of the 2 balls, you see the response is very chaotic. So we leverage the data, which are actually the high resolution, high speed camera videos recorded by the IBM group a few years ago. And we first extract the position of the trajectory. And further, we calculate the corresponding angles of the 2 objects, so theta 1 and theta 2. And afterwards, we take the theta 1 and the theta 2 as our measurement data to discover the corresponding equation, the governing equations. So we see here, for the 2 angles, there are some discontinuity. If we convert the theta values into the minus pi to pi range, we see some discontinuity here. And here I show the discovered equations. We firstly assume, the relationship between the derivative of the angular displacement and the velocity. We assume this relationship is known. That's essentially the relationship between displacement and velocity. However, the governing equations for the acceleration terms are unknown. So we try to discover, these complicated equations. And these are the discovered equations based on a very large scale library of candidate functions we have designed. And in particular, we found that comparing these discovered equations with the formulations derived from Lagrange method, we found, all of these terms agree with the reference very well. Here we also found that there are some additional terms, that are unknown terms, that are treated as unknown terms if we compare those formulations with the Lagrange-based formulation. And after careful, analysis, we found these 2 terms are actually the damping terms. because if you go back and take a look at the two systems, there are some damping here, right? So these are the two damping terms discovered by this approach. That actually matches our common understanding. These are the examples. So let me discuss briefly on the bottlenecks or the limitation of the PIN approach or physics-informed supply and learning approach with sparse regression for equation discovery. So here we have to design a good candidate function or candidate library in order to discover the equation correctly, right? So if we lack some terms in the library, then the discovered equation will be incorrect. So this is the first challenge: how to design a inclusive library, but not necessarily large space one will be a key challenge. The second is, if we increase the library dimension, then the computation cost will increase dramatically. Okay, this is another challenge. Third is the limited capacity of this kind of formulation. So we see that the formulation of the ODE or PDE is based on a linear combination of different basis functions, right? So this formulation cannot represent some formulas which are very complicated. For instance, if we have a formula like this, okay, so essentially the linear combination cannot describe such a formulation anymore. So this is another challenge. And the next one is, we also are faced with the challenge of dealing with the sparsity term here. Even though the alternating direction optimization approach works, however, we also found that if we have less data or higher noise, we observe some false positives. That means the library-based approach will have some bottleneck there, right? So how to address all of these challenges and issues? So we are inspired by the passing tree approach, because based on the methods in the literature, we know that every single mathematical formula can be represented by a passing tree, or some other times people call it expression tree. Okay, so instead of discovering the equations directly, we try to find the corresponding passing tree, then turn this into the governing equation. So that's the general idea behind it. So to this end, we develop a physics-informed symbolic reasoning approach that consists of 4 different components. The first one is the computation rules. Second is path tree. The third one is a symbolic variational autoencoder. The last one is the discovery of governing equations. So I'm sorry this page is a little busy, but I will explain one by one. So firstly, let's take a look at the computation rule. So we know that any mathematical formula can be represented by unary or binary operators, the combination of different operators, right? So here I list some very commonly seen operators, such as plus, minus, times, division, square root, sine, cosine, log, and some other derivative, etc. So all of these are commonly seen formulas. So almost 90% or even more, 95% of the commonly seen mathematical formulas can be described by this finite set of mathematical operators. So we try to firstly define these computation rules based on the symbolic operators. And later on, we generate many different path trees in order to train a symbolic autoencoder. Later on, I will introduce. So based on the computation rules, we can generate randomly the path trees to represent any possible mathematical formulations. Okay, so the number of the generated pattern trees could be very large, 10 to 6 to 10 to 7, on the order of 10 to 6, 10 to 7. Okay, so there are some approach introduced in this paper, the deep learning of symbolic mathematics paper published in 2019 in ICLR. So these two authors introduced a nice approach based on random probability theory to generate the expression trees. And we follow their approach and generate a large number of trees. Afterwards, we turn these trees into digits so that the machine can recognize, right? So we convert the past trees into one-hot matrices. So the one-hot matrices consists of 2 dimensions. So one is the tree depths. The other one is the operators we have used to construct the past trees. For instance, in the operators direction, we have a plus, minus, sine, cosine, etc. In the tree depths, if we look at this tree, it has a certain depths, right? We follow the transversal direction and we can actually count the depths. And this is the prescribed depths in the generation of the past tree. So after converting the past trees into the digits, one-hot digits, we input it into a symbolic autoencoder, variational autoencoder, essentially. That consists of the encoder based on LSTM and the decoder also based on LSTM. So we try to convert the discrete digits, 0, 1 digits, into a continuous space. And this kappa is actually continuous latency space. And we try to actually train this symbolic autoencoder such that later on we can only use the decoder to discover the equations by changing the kappa values. Okay, if we change a kappa value in the continuous latency space, it will generate a equation here. Okay, so
can
that's
I ask
the general.
a quick question? This is Yan Zhong from Brown.
Yes.
I'm wondering if the tree structure is unique. It seems does not.
You're right. It is not unique. That's a very good question. So here, that's why we train the autoencoder here in a probabilistic way rather than a deterministic way. So instead of find a deterministic one-to-one mapping relationship, we find a manifold in the latent space. So there's a likelihood that, let's say we get a distribution of this kappa. When we do the sampling, so later on, I will introduce, the approach, the probabilistic approach we developed. So when we do the sampling, there will be a finite number of possible equations that could be used to describe the same data set. That's the approach behind it. But this is a very good question. It is not unique.
Yeah, then are you giving some of the constraint on the maximum tree depth?
Yes.
Okay, that makes sense. Okay, thank you.
Yes. For instance, here we give 20, the number of 20, because we want to keep the formula parsimonious. Of course, we can generate, let's say, the trees all the way up to the order of 30, but the equation will become very long. So we don't want to see such an equation, because in many dynamical systems, no matter it's PDEs or ODEs, we see the equation very parsimonious, only with several dominant terms, right? So that's the rationale behind it when we generate the past tree. Yeah.
Thank you.
Thank you. And the last component is the discovery of the governing equations. So this is for this part, it shares some similarity with the PIN, with the sparse regression approach. So here we use a deep neural network to represent the solution, let's say U1, U2, U3, or UVW. And we can construct this phi matrix, this phi vector. This phi vector is actually determined by this decoder. So you see here, kappa is trainable, and this theta for the deep neural network is also trainable. We train these 2 parameters at the same time, okay? And theta is used to represent the solution. Kappa is used to reconstruct the expression, okay? And the unified physical law will be constructed by this kappa constructed expression and also this neural network output, okay? So we formulate the entire approach using variational inference. So let me let us recall the, the procedure for the first two steps, firstly. So firstly, we generate a vast number of past trees as the training data. Second, we train the symbolic variation autoencoder using variational inference, so that instead of getting a deterministic value for the latent space, we get a distribution for this kappa. And afterwards, we apply the hierarchical variational Bayesian inference to train the neural network parameter theta and also the kappa distribution, kappa value. Afterwards, we can get the approximated posterior distribution of kappa and theta. And we can sample the kappa in order to get the closed form equation. So since here kappa is the distribution, of course, we can sample a group of equations. And these equations are pretty similar, actually, based on our test. And afterwards, we can evaluate the loss function and identify the best equation that will be used to describe our measurement data. So let me show you an example here. This is the Gray-Scott reaction diffusion equation used to describe the chemical biological system as well. And the measurement data includes some low resolution, low speed snapshots. And the underlying governing equations are shown here for U and V equations, including the diffusion and reaction terms. Especially for the reaction terms, they are nonlinear. And the measurement data here only consists of 20 low resolution snapshots. So here, this is the U snapshots, V snapshots. And we apply this approach to discover the equations. And we see the discovered equations are shown here. And the ground truths are listed here. And they match each other very well, including both the corresponding terms and also the coefficients. They match all very well. The total prediction error for the full field response is about 4% here. But this is still an ongoing study. We try to test this approach on more complicated governing equations, as I showed previously with some exponent terms, sine term, sinh term, coach term, or some other terms. And this is still an ongoing study. And we found that this approach has better potential to address the issues I discussed previously associated with the PIN sparse regression approach. So finally, some concluding remarks. Here in this presentation, I discussed several different physics-informed learning machines for discovery of complex systems, including both the discrete dynamic system and the continuous dynamic systems, whose governing equations are ODEs and PDEs. So we consider sparse and noisy data in the discovery. And overall, based on the examples, numerical examples and experimental examples, we see this approach is robust against the data noise and scarcity. And there are some remaining challenges we are trying to address. For instance, uncertainty quantification with noisy data, sparse data. And we try to extend such approach to some real-world applications. And in the meanwhile, we are also interested in multi-scale discovery, because we know that for many systems, the governing equations might possess different scales, right? So we try to extend this approach to account for multi-scale effect for the discovery of equations as well. So overall speaking, we try to leverage some limited prior knowledge of physics and use the physics to encode or inform the deep learning approach, and further use the physics-informed learning machine to discover the physics again. So that's like a loop. And finally, I would like to acknowledge my group members and also sponsors from NSF and some other agencies. And here I listed the two papers on arXiv. So we also have the source code in the GitHub. Please feel free to download them and let me know if you have any further questions. The second paper has been accepted by the IGSAI paper conference this year. Thank you very much.
All right, thank you, Professor Sun. So, are there any questions from the audience?
Yeah, I have a question.
Sure.
Sure.
Yeah, could you go back to your symbolic algorithms for? Yeah.
This one?
Yeah. So I want to know like the difference. So in the original Facebook paper, the original deep learning for symbolic mathematics paper, they also used a tree to represent.
Yes.
Yeah, and they treat the input of the neural network as a sequence. So they basically build a sequence to, and maybe a sequence to sequence, but yeah, they treat the input as a sequence. So what you did here, could you tell me, could you elaborate the difference between like your method, you added encoder decoder, you used the variational autoencoder, yes.
Sure.
They didn't do that, but
yeah.
Did you
good
treat
question.
the input as the sequence as well?
So it is a sequence. Firstly, let me comment a little bit on the Facebook paper. They use a sequence to sequence model with attention mechanism. That's their method. But here we convert this to one hot matrix. So for instance, here the columns here are representing the different computation rules, plus, minus, sine, cosine, all of these, okay? Then this is tree depth. So if we look at this tree, okay, and from this is the terminal node, right? We count from the terminal node to this S. S is actually the unary operator. And afterwards, we have this M operator. M is corresponding to a binary operator. We actually, if we have a value here, let's say, we put a 1 in the one hot matrix. Otherwise, we put zeros. Okay, so this is like an embedding, of the sequence into a 0-1 matrix. So you can view this as an embedding approach, which is different from the sequence to sequence model, but they share some similarity.
Okay.
I hope I answer your question.
Yeah.
I have a question. Could you kindly go to your Gray-Scott model slide, please?
Which one? I'm sorry.
Gray-Scott model.
Oh, okay.
Yeah, here, how about if you have widely varying diffusion coefficients? Does your scheme still works? Have you tried that?
Very good question. So here we consider we tried different coefficients. So if we have a very, very small coefficient here, let's say 10 to minus 5,
yeah,
this approach will fail essentially.
Right. I'm glad you mentioned that. Yes.
I forgot to mention that, but this is a very good question. We tried the coefficient here on the order of 10 to minus 2, essentially.
Right.
Yes, you're right.
And any suggestions or any thoughts on it, or how we approach that?
Yeah, we tried and to play with the coefficient of the diffusion. So in the discovery, we tried another case here. I didn't show that. So we try to say the diffusion term is known. However, the coefficient is unknown. And we basically exclude this in the discovery, of the unknown form of the equation, because we think we assume these two terms are known. Later on, we apply an activation function of this mu term.
I see.
For instance, the sigmod, and the sigmod produces the range from 0 to 1, right? Then we multiply a coefficient in front of the sigmod function as 10 to minus 5. Then instead of identifying this mu parameter directly, we identify the parameter inside the sigmod function.
I see.
That helps.
Oh, okay. All right.
Yeah.
Well, thank you very much.
On that.
Yeah, thank you. I'll contact you, send you an email, and then we can discuss further. Thank you.
Thank you. Yeah.
Great. Any other questions? Well, if there's no more questions, please join me in thanks our speaker once again. Thank you, Professor Sun. Very nice talk.
Thank you.